Regrounding the grounded conductor downstream of the first disconnect is problematic for several reasons, primarily related to code violations and technical issues. Firstly, referring to code violations, National Electrical Code Section 250.24 FIF requires the equipment grounding conductor to be continuous throughout the entire grounding path. Regrounding the grounded conductor downstream of the first disconnect would violate this requirement. Also, National Electrical Code Section 250.124 prohibits bonding the neutral conductor to grounded objects downstream of the service. Regrounding the grounded conductor would effectively create a bond between the neutral and grounded objects. Moving on to technical problems. 1. Voltage potential. Regrounding the grounded conductor creates a parallel path for neutral current, reducing the current flowing through the intended grounding path, for example, the service ground rod. This can result in a higher voltage potential on the neutral conductor, potentially causing equipment damage or electric shocks. 2. Ground loops. The regrounded neutral creates an additional path for fault current to flow. This can result in ground loops, where current flows through unintended paths, such as through metal conduit or piping, creating electromagnetic interference and potential fire hazards. 3. Ground fault detection. Regrounding the neutral can limit the ability of ground fault circuit interrupters, known as GFCIs, to detect and protect against dangerous electrical faults. This is because the GFCI compares the current flowing in the hot and neutral conductors, and the regrounded neutral would alter this comparison. 4. Neutral ground potential rise. In the event of a fault on the grounded conductor downstream of the regrounding point, the current flowing through the regrounded neutral can cause a significant voltage rise in the neutral conductor. This rise in voltage could damage sensitive electronic equipment connected to the circuit. 5. Corrosion. Regrounding the neutral can introduce a galvanic cell between the grounding rod and the new ground connection. This can accelerate corrosion on the grounding rod and reduce its effectiveness. Considering these points, regrounding the grounded conductor downstream of the first disconnect is a dangerous and code-violating practice that can lead to serious safety hazards and equipment damage. It is essential to maintain a continuous grounding path throughout the entire electrical system to ensure proper grounding and prevent electrical faults. The intended grounding path ensures that in the event of a fault, the current will flow back to the source, tripping the circuit breaker or fuse and disconnecting the power. When you introduce additional ground points downstream, you create alternative paths for the current. This division of current can lead to several problems. Firstly, the ground fault protection devices, such as circuit breakers and GFCIs, may not operate as intended. These devices are designed to detect imbalances in current between the hot and neutral conductors. If some of the fault current is diverted through the unintended ground path, the imbalance may not be large enough to trip the protective device, leaving a potentially dangerous situation unresolved. Secondly, the unintended ground paths can create ground loops. These loops can carry stray currents that can interfere with sensitive electronic equipment, causing malfunctions or even damage. Ground loops can also create electromagnetic interference, which can disrupt communication signals and other electronic devices. Thirdly, regrounding the neutral can lead to voltage drops along the neutral conductor. This is because the neutral current is now divided between multiple paths, increasing the overall impedance of the neutral circuit. Voltage drops can cause equipment to malfunction or operate inefficiently, and in severe cases can even damage equipment. Furthermore, the additional ground points can create a difference in potential between different parts of the grounding system. This potential difference can cause current to flow through the earth, which can be a shock hazard. It can also accelerate corrosion of underground metallic structures, such as pipes and conduits. The National Electrical Code provides specific requirements for grounding and bonding to ensure the safety and reliability of electrical systems. These requirements are based on established engineering principles and are designed to minimize the risk of electrical shock, fire, and equipment damage. It is crucial to follow these requirements carefully when installing and maintaining electrical systems. In the specific scenario described, where a subpanel has a 4-wire feeder and the neutral is isolated from the equipment grounding conductor, it is particularly important to avoid regrounding the neutral. The 4-wire feeder provides a dedicated equipment grounding conductor, which is connected to the grounding electrode system at the service entrance. This dedicated grounding conductor provides a low impedance path for fault current to flow back to the source, ensuring that ground fault protection devices will operate correctly. Regrounding the neutral at the subpole would create a parallel path for fault current, which could compromise the effectiveness of the grounding system. To summarize, the potential problems associated with regrounding the grounded conductor downstream of the first disconnect include code violations, compromised ground fault protection, ground loops, voltage drops, potential differences, and corrosion. It is essential to maintain a continuous and dedicated equipment grounding conductor system to ensure the safety and reliability of electrical systems. By adhering to the National Electrical Code and following established grounding practices, electrical systems can be designed and installed to minimize the risk of electrical hazards. One must also consider the effect on surge protection devices. A properly installed surge protection device diverts excess voltage to ground, protecting equipment from damage. If the grounding system is compromised by downstream regrounding, the surge protection device may not function effectively, potentially leading to equipment damage during a surge event. Another important consideration is the coordination of overcurrent protection devices. Circuit breakers and fuses are designed to protect circuits from overloads and short circuits. If the grounding system is compromised, the overcurrent protection devices may not operate as intended, potentially leading to equipment damage or fire. Furthermore, regrounding the neutral can create confusion and make it difficult to troubleshoot electrical problems. When multiple ground paths exist, it can be challenging to determine the source of a fault or the cause of a malfunction. This can lead to increased downtime and higher repair costs. In addition to the technical problems, regrounding the neutral can also create legal and liability issues. If someone is injured or property is damaged as a result of a compromised grounding system, the responsible party may be held liable. This can result in significant financial losses and legal penalties. Therefore, it is essential to avoid regrounding the neutral and to ensure that the grounding system is installed and maintained in accordance with the National Electrical Code and other applicable standards. Regular inspections and testing of the grounding system can help to identify and correct any potential problems before they lead to serious consequences. A properly functioning grounding system is a critical component of any electrical system. It protects people and property from electrical hazards and ensures the safe and reliable operation of electrical equipment. Therefore, it is essential to take the time to understand the principles of grounding and to follow established grounding practices. The National Electrical Code provides detailed guidance on grounding and bonding requirements. It is important to consult the National Electrical Code and other applicable standards when designing, installing, and maintaining electrical systems. In addition to the National Electrical Code, there are other resources available to help understand grounding and bonding principles. These resources include textbooks, training courses, and online resources. By taking the time to learn about grounding and bonding, one can help to ensure the safety and reliability of electrical systems. Moreover, the consequences of improper grounding can be severe, including electrical shock, fire, and equipment damage. It is therefore essential to take grounding seriously and to follow established grounding practices. A properly functioning grounding system is a critical component of any electrical system, and it is essential to ensure that it is installed and maintained correctly. By following the National Electrical Code and other applicable standards, one can help to protect people and property from electrical hazards. The integrity of the grounding system is paramount for safety and proper equipment operation. The continuous grounding path, as mandated by the National Electrical Code, provides a low impedance route for fault current to return to the source, enabling rapid operation of overcurrent protection devices. Introducing additional ground points downstream disrupts this carefully designed system, creating potential hazards and compromising the overall effectiveness of the electrical installation. It is important to remember that the grounding system is not just a safety feature, it is also an integral part of the electrical system's performance. A properly grounded system helps to reduce electrical noise, improve power quality, and prevent equipment malfunctions. By maintaining a continuous and dedicated equipment grounding conductor system, the reliability and efficiency of the electrical system can be enhanced. In conclusion, regrounding the grounded conductor downstream of the first disconnect is a practice that should be avoided. It violates code requirements, creates technical problems, and compromises the safety and reliability of the electrical system. By adhering to the National Electrical Code and following established grounding practices, electrical systems can be designed and installed to minimize the risk of electrical hazards and to ensure the safe and reliable operation of electrical equipment.